In this video, we're going to be doing a rolling motion problem. So let's say that we have this object that is going to be rolling down this inclined plane, and this object, we can draw the FBD for this. When you draw the FBD for this, you have a normal force that is going to be acting at the point of contact, which is going to be the point where the ball is going to be resting on the inclined plane, not from, and you want to draw this perpendicular to the plane because the normal force is always perpendicular to the point of contact. You don't want to draw a normal force that's like this just because it's straight up, because that is not going to be perpendicular to the point of contact, because our point of contact is not directly on the ground, it's actually at an angle. So you also have in this object, you have a static friction force because this object isn't moving yet, so it's going to be static friction that's holding the object in place. In addition, you have a weight force, aka your force of gravity, which is your mass times your gravity, your gravitational acceleration, and you can break that up into components. So you have a vertical component here, Fy, aka your force that is going to be perpendicular to your plane, and you have your Fx, which is going to be the force that is parallel to the plane, and Fy is equal to mg cosine of theta, because h, which is your weight vector, is going to be your hypotenuse, and then this is your adjacent side that is related by the trigonometric ratio of cosine, and Fx is related by mg and then sine of theta. So now what we can do is we can look at the Newton's equations for each of these directions. So for our parallel forces, the summation of these is going to be in the horizontal direction. We have mg sine of theta, which is going to be down. So this is going to be our direction of acceleration. So we're going to make mg sine of theta positive. And then we have negative Fs is equal to ma. And we can also write this as summation of Fx. Now here, for summation of Fy, we are going to have our summation of Fy is going to, our forces that are perpendicular are going to be equal to 0. That's because we only have movement, we only have a force that is unbalanced in the direction that is parallel, because our vertical forces are going to equal each other. So here n is equal to mg cosine of theta. Now for torque, we are going to have rotation about the center. So we have to ask ourselves, which forces cause a torque? So in our scenario, that's not going to be Fg, because it acts at the center. And when it's acting at the center, that means that the R, your lever arm, is going to equal to 0. And if your arm is equal to 0, that means that your torque is going to equal to 0, because torque is equal to F r sine of theta. And if you just plug in F times 0 sine of theta, it's going to make the whole entire torque equal to 0. So you're only going to have torque from friction only. You're going to have torque is equal to your force times your lever arm, sine of theta. And here, your force is going to be the force of friction, and your R is going to be equal to your radius, and that is going to be set equal to torque. And then you can set your summation of torque equal to IA, which we did up there. So we can take this, and you can write that F, your force of friction, times your R is equal to your I times alpha. We can call this equation 2. And you also don't have torque from Fn. That's because line of action of Fn is going to pass through the center. Now, what's the rolling without slipping condition? That's when acceleration, your translational acceleration, is equal to your angular acceleration times your r. So if you rearrange that, that's angular acceleration is equal to a divided by r. So now that you have isolated alpha, you can actually take this rearranged form of alpha And you can substitute this into this equation here. And if you do that, you get this new form. That is F friction times R is equal to IA over R. A over R. So after this, you can just rearrange for the force of friction, which is going to be IA over R squared, because you divide both sides by R. And we can call this our third equation. Now, after this, we can look back at equation 1. So in equation 1, we had positive mg sine theta is equal to negative force of static friction. We'll actually just call this F, and we'll call this also to just be F as well, to keep our variable consistent. And this will also be F. This will also be F. So when we're here, we can substitute into our equation 3. So this is going to be mg sine of theta minus what we have as our friction. So this is our third equation, right? So you can take F and you can substitute that in for that F. That means that you have I times A over R squared is going to equal to your mass times acceleration. After this, you're going to just solve with your algebra carefully. We're going to move everything with A to one side. So this is going to be minus or plus IA over R squared plus IA over R squared. That's going to cancel out. You're going to have mg sine of theta is equal to your new side. And what we notice on this side is we have A in both of the terms, so you can factor out that A. You have m plus I over R squared is equal to mg sine of theta. After this, what you can do is just divide both sides by m plus I over R squared. And then after this, your A is going to equal to mg sine of theta is equal to m plus I over R squared. So if you divide your numerator and your denominator by m, if we take this, divide that by m, take this, divide that by m, then you're going to be left with A is equal to g sine of theta 1 plus I over m R squared. And this is the derivation for the acceleration on this rolling plane. So we use our translation along the incline, we use our perpendicular direction, and we also use rotation and the rolling condition. So usually what you have is FG tries to accelerate with an mg sine of theta. But here, because we have rolling motion, part of that goes into our linear and our rotational motion. So then your acceleration is going to become this form that we just derived here. So now let's do some practice problems that demonstrate this concept. So a solid sphere with a mass m and radius r is released from rest at the top of an incline at an angle of theta. It rolls without slipping. What is the acceleration of the sphere down the incline? So for this problem, we can find this by examining what is the moment of inertia. So for this rolling object down an incline, you have, again, the weight mg downward. You have the normal force that's perpendicular to the plane, and you have static friction that's acting up the incline. So your gravity component that is down the incline is going to be mg sine of theta, and then up the incline, or the gravity component into the incline, perpendicular to the incline, is going to be your mg cosine of theta, like we saw earlier. So then again, we just do the summation of your fx is equal to your mass times acceleration. You have mg sine of theta, which is going to be, we're going to choose acceleration, downward, even though it's not accelerating here because it's at rest. But we're going to choose that to be the positive x direction and upwards to be the positive y direction. So this is going to be subtracted by negative f, which is acting up the incline, but that's our negative direction here. That's going to equal to your mass times your acceleration. Now, for our Newton's second law, that's perpendicular to the incline, you have Fy is equal to 0. You have your normal force, which we're going to consider to be up, and we have mg cosine of theta is equal to 0. So n is equal to mg cosine of theta, like we saw earlier. This is correct, but we don't really need it for acceleration. We only really need the horizontal Newton's equation. So now again, for the rotational, we have torque is equal to I acceleration, and this is about the center of mass. So only our friction is going to cause torque. So you have Fr is equal to I times your angular acceleration. So for I of the sphere, you have that it's equal to 2 over 5 m times radius squared. So you have Fr is equal to 2 over 5 m times radius squared times your angular acceleration. So your no slip condition is A is equal to alpha times r. So rearranging, that's the alpha equals to A over r. You can substitute that back in as well. You can actually leave these over here since it's kind of getting a little bit crowded. So you have again Fr is equal to 2 over 5 m r squared, but now you are going to use your A over r instead of alpha. So here you had I, and then here we have alpha. After this, you can simplify. So Fr is equal to 2 over 5 m, and you have one of these r's are going to cancel out. So you have r times a. After this, you can divide both sides by r and see that they're both on either side, so you can just cancel. F is equal to 2 over 5 m times a. So now that you have F, you can substitute this back into our translational equation. So we can move this over a bit. That was there. So now that you have what F is, you can substitute this F value into this equation here. So this is going to be mg sine of theta minus 2 over 5 mass times acceleration is equal to ma. Now we just move our friction term to the right, plus 2 over 5 ma plus 2 over 5 ma, and this cancels out. So you have mg sine of theta is equal to mass times acceleration plus 2 over 5 mass times acceleration. So mg sine of theta, you can rewrite that 1 over 1. This is basically saying you have something multiplied by 1. You can rewrite 1 as 5 over 5. So that makes your addition visually easier. That's going to be you having 5 over 7 ma. Or this is going to be you having 7 over 5 ma. Or no, 5 over 5 ma. So then if you add those, you get 7 over 5 ma. And this is going to give you 7 over 5 ma. So then you have A is equal to 5 over 7 g sine of theta. So your answer is 5 over 7 g sine of theta. So you have a solid sphere, mass m, that is released from the top of an incline, and it rolls without slipping. What's the acceleration of the sphere down the incline? I think this is the same question repeated twice. We can do this problem. A solid cylinder, mass m, radius r, rolls down an incline at angle theta without slipping. What is the magnitude of the static friction force acting on the cylinder? So you have Newton's translational law, which is summation of forces, is equal to mg sine theta minus F is equal to ma. So rotationally, you have the summation of torque is equal to I alpha. Summation of force here is equal to mass of acceleration. So what you do is you have Fr is equal to I times alpha. I is equal to 1/2 mr squared. Fr is equal to 1/2 mr squared alpha. A over rolling condition, you have A is equal to alpha times R. So alpha is equal to A over R. You substitute that into torque, you have Fr is equal to 1/2 mr squared times A over R instead of alpha. Then you can cancel one of those R's like you did earlier. You have Fr is equal to 1/2 mRA. You can divide both sides by R. You get F is equal to 1/2 times mass times acceleration. You can substitute this equation, which we'll call 3, into 1. And we're going to call this equation 1. So you're going to have mg sine of theta minus 1/2 mass times acceleration is equal to ma. So mg sine of theta is equal to 3/2 ma. So A is going to equal to 2/3 g sine of theta. To find friction, you have F is equal to 1/2 ma. So then we return to this form. F is equal to 1/2 ma. This is when we're finding friction. So we have that A is equal to 2/3 sine of theta. We're going to take this, and you're going to substitute that in for A here. So your friction is equal to 1/2 m, and then that will be 2/3 g sine of theta instead. So this is equal to 1/3 mg sine of theta. That's because this 2 cancels out. That's F. So that is your answer. 1/3 mg sine of theta. That's A. Or that's A. A object rolls without slipping down an incline with acceleration. A is equal to 2/3 g sine of theta. What is the object's moment of inertia in terms of m and r? So we're going to use our formula that we derived earlier, which is A is equal to g over sine of theta. This is for Newton's law for when you are rolling down an incline. So that's g sine of theta, 1 plus I over m r squared. A is equal to 2/3 g sine of theta, which we have up here. So if you have A, you can set these equal to each other by using this equation. We're going to set g sine of theta, 1 plus I over mr squared equal to 2/3 g sine of theta. So you can, on both sides, see you have g sine of theta in the numerator. You can cancel that 2/3 g sine theta out. You're going to be left with 1 over I, 1 over 1 plus I over m r squared. That's equal to 2/3. Now you solve this algebraically. We can take the reciprocal of both sides. So this will turn into 1 plus I over mr squared is equal to 3/2. If you subtract 1 from both sides, this is actually meant to be a 1. You have I is equal to, I over mr squared is equal to 1/2. 1 is equal to 2/2. So that's 3 minus 2, which is equal to 1/2 m, or 1/2. And then after this, you can multiply both sides by mr squared. If you do that, then you get I alone is equal to 1/2 mr squared. So that means that you have a solid disk or solid cylinder based off of your moment of inertia. So your answer is B. A solid sphere rolls down without slipping down a 30-degree incline. What is its acceleration? So for a solid sphere, A is equal to 5/7 g sine of theta. So we know that here our theta is equal to 30 degrees. So if you have sine of 30, you can do A is equal to 5/7 times 9.8 sine of 30. Sine of 30 is equal to 1/2. So A, if you plug this in, that's 3.5 meters per second squared. And that's equal to B.